Good morning, everyone. Let's get started with our warm-up for today. There is a graphic organizer to go along with today's lesson that I'm posting right now in the chat, but it's also on Canvas. So what I first want you to do is on your graphic organizer, I want you to write down if you've ever seen a runaway truck ramp before, and I want you to write down what you think they do. So let's take a few minutes for people to join on in, and I want you to write down what you have if you've ever seen a runaway truck ramp before and what you think they do. I'm going to post a link to the graphic organizer again. It's right here. But yeah, you're in graphic organizer. I want you to write down if you've ever seen a runaway truck ramp before, and I want you to write down what you think they do. There are not, I don't know if there's a lot around here. There's definitely a lot when you're driving down the Highway 5 towards LA. I've seen a lot there. And someone in first period told me that you see a lot of these on the I-80 going up to Tahoe. So you may or may not have encountered one of these before. But this is just a chance for you to write down if you've ever seen one and what do you think they do. And we'll move on in a minute. So this is just to jog your brain and get thinking about the topic. They're actually quite interesting, quite fascinating, if I do say so myself. Um, okay, so what we're doing today is we're going to be talking about forces at angles. In terms of due dates, I want you to finish your self-assessment for the force data analysis by this Thursday, Friday. If you can't do it by then, that's okay. I'm flexible with that. But the sooner you do it, the sooner I can give you feedback, and the sooner that it'll be graded. So do what you can there. The second one, don't worry about the second thing. We won't start that today. Okay. So today we're going to be talking about runway truck ramps, and we're going to talk about what are they and how do they work. So to first get our brains going here, we are going to watch a video of a runaway truck ramp being used in action here.
These runaway truck ramps have been a huge topic of discussion ever since this video came out showing Rohel Aguilera Medeiros skipping that final runaway truck ramp on I-70.
Hold on, it's not
just minutes.
It's not showing. Hold on, give me a second. There we go.
Well, these runaway truck ramps have been a huge topic of discussion ever since this video came out showing Rohel Aguilera Medeiros skipping that final runaway truck ramp on I-70 just minutes before that deadly crash.
Definitely had my adrenaline going.
as he came through the Eisenhower Tunnel heading west.
He was starting to get upwards of 80, 85 miles an hour.
Jesse Terrell knew something was wrong.
The smell was horrible. Just that burning rubber, and that's when I kind of knew, oh, his brakes are now gone.
Watching this truck climb a runaway truck ramp, swerving all the way to the top.
His trailer was, doing this all the way up, and I was pretty impressed with how he kept control.
Local tow companies tell the problem solvers it's a scene that plays out roughly once a week on this ramp.
They apply their brakes for too long, and they burn the shoe out from the drum.
Charles Sergel works the I-70 corridor repairing big rigs and says that number should probably be higher.
And a lot of the drivers would rather come to a complete stop versus hitting one of those ramps and damaging their truck. Getting a tow out of one of those ramps is about $4,500 bucks, depending on how deep it is, depending on the damage. It's expensive.
A cost he tells truckers is well worth the lives that can be saved.
Absolutely, yeah. It's better than hurting people. In any way possible that we can assist and keep the highway safe, that's what we're going to do. We need to tell these drivers that they need to use the ramps. Stop trusting their brakes when they're smoking.
Jesse Terrell is glad this trucker made the choice they did.
If not, at the bottom of that hill, there's a really sharp turn right over the Silverthorne Bridge, and he would not have made it.
Now, State Patrol says there is a common misconception among truckers that they'll be punished for using these ramps.
So I just wanted you to quickly jot down what you observed and how you think this ramp works. So take a minute or two just to quickly jot that down.
Well, these runaway truck ramps have been a huge...
Okay, so what are these runaway truck ramps? So these runaway truck ramps are specifically designed to safely stop trucks that have brake failure, as you saw in the video. A lot of the times, this mostly happens during downhill sections when truckers have to apply their brakes. And when you apply your brakes for a significant amount of time, they can burn out and have potentially fail. And so when their brakes are failing, it's very, very, very dangerous, and there needs to be a way to stop them. There's no easy way to stop a truck that is failing, that brakes are failing, because they're so big and so massive. So you really have to sort of resort to extreme measures, and that's sort of what these runaway ramps are for. So the way most of these ramps are designed is they use a combination of ramps that go upwards and sand and gravel. So the ramps slow down trucks with gravity, right? So when a truck goes up a ramp, the truck naturally wants to slow down because gravity is pulling it down. And additionally, the sand and gravel of the ramp sort of allows the truck to sort of sink into the ground. Instead of just like driving over it like a normal path, right? It sort of sinks it. It's almost like a ball pit, right? It's very hard to move quickly in a ball pit because all your energy is being used to sink into the ball pit. So you see these runaway ramps a lot when you're on a downhill section of so these usually occur on freeways when there's a lot of steep slopes, when a lot of downhill slopes, especially when there is a portion where there's like a sharp turn or when there's like a stop required. So that's when you see these runaway ramps most frequently. So what I want you to do now is I want you to quickly answer this quick poll here. I want you to answer which of these forces do you think are present when a truck with brake failure is going up a ramp? So when a truck with brake failure is going up a ramp, what forces do you think are present? So this is a true multiple choice question. Do you think there's friction? Do you think there's normal force? Do you think there's gravity? Do you think there's applied force? Which of these which of these do you feel like happen here? We got 30 people here, so let's try to get 30 responses, 30 poll answers, try to get 100% participation. We're currently at 19 out of 30, which is 63%, but we are A++ students, so let's shoot for that 100. So we need about 10 more responses. If you're one of those 10 who hasn't responded yet, please do so. Let's shoot for which of these forces do we feel like apply here? Do we feel like there's friction? Do we feel like there's normal force? Do we feel like there's gravity? Do we feel like there is applied force? Let's take another 20 seconds or so. Let's get these last 4 votes in. At 27 out of 30, just need 3 more. So out of these 4, there are 3 forces present here. There is the force of friction, there is the normal force, there is gravity, but there is no applied force. So the first 3 are there, the first 3 forces are there, the 4th one, the applied force, is not there. So in your graphic organizer, I want you to jot down, where do you think the force of gravity comes into play? Where do you see gravity here? Then I want you to write down, where does the normal force come from? Then I want you to write down, where does the friction force come from? And then for the 4th one, I want you to think about, why is there no applied force here? So you may not know the answer to all of these, that's okay. I want you to write down what your thoughts are, why you think where these forces come from, why some of these forces aren't here. It'll take about a few minutes for you to just quickly jot down where these forces come from and why some forces are present and why some are not present. So where do you think the force of gravity comes into play? Where do you feel like the normal force comes from? Where do you feel like the friction force comes from? And why do you think there is no applied force here? Why is there no applied force here? Good question. That one's probably the trickiest one. I think the other 3 are, a little bit more straightforward. Take another minute or so for you to jot down where you think these forces come into play, where you think gravity, where you think the normal force. So where do you see gravity in this problem? So there are actually 2 ways you can see gravity, but the main way I like to think about it is that as the truck is going up the ramp, gravity is effectively pulling it down. So it effectively slows down the truck's velocity as it goes up, right? This is, if you think about it, when you roll a ball up a hill, it just starts to slow down and eventually it comes back down. So the exact same phenomenon with gravity. You can also think of gravity sort of allows the truck to sort of sink into the gravel. That is also where you might see gravity. So those are sort of ways that you can see gravity here. The normal force is just basically the force that the ramp exerts to prevent the truck from going through the ramp. If there was no normal force, the truck would just like go through it like a hot knife through butter, right? There needs to be some sort of normal force to support the truck from going through the ramp. There is friction because the gravel and or the sand, right? They resist the truck's motion and they work to slow down the truck's velocity. So that's sort of where you see friction. The hardest one to understand is probably the applied force. There is no applied force here because the only way that you can see applied force is probably through the truck's engine or the truck's brakes. If the truck is brake failure, then the brakes are not working, so there can't be any applied force there. And if the truck is struggling because they can't brake, they're not really going to be pushing the gas pedal either. So the gas pedal, there's not going to be an applied force pushing it forward either. So the truck just basically is at the mercy of gravity. So there's just no applied force coming from the truck. And so the three main forces you'll see here are gravity, the normal force, and the friction force. Again, gravity is where you see is basically what helps slow down the truck as it's going up. It pulls down the truck down. It decelerates the truck. The normal force is the force that the ramp exerts to prevent the truck from going through the ramp. The friction is from the gravel and or the sand, the ramp that resists the truck's motion and works to slow down the truck's velocity. And then there is no applied force here, but because the truck's brakes aren't working and because the driver is not pushing the gas pedal. So now I want you to hypothesize what happens when a truck is by the velocity, which indicates that the truck is going up. So I want you to write down what direction do you think the net force acting on the object is? So what direction do you think the net force acting on a truck going up a ramp is? And then I want you to see if you can explain why you think so or how do you know. And I also want you to draw an arrow on the diagram indicating which direction you think the net force is in. What direction do you think the net force is in? Draw an arrow for that. And why do you think the net force is in that direction? Or how do you know that it's in that direction? Anyone have any ideas what the net force is or which direction it's in? What direction the net force is? Is it straight up? Is it down? Is it up the ramp? Down the ramp? To the side?
It's parallel to the ramp, right?
We have one person who says it might be parallel.
I think
one
it's
person-
perpendicular.
Interesting. Why do you think it's perpendicular?
To like the floor, quote unquote, because that's how normal force works.
That is true. That is how the normal force works. Daniel, can I ask you why you think it's parallel to the ramp?
I think it's parallel because there's also like since the I'm going by like the picture,
Mhm.
it shows like the directions moving up, I'd assume like when it slows down, it would end up going in the opposite direction.
Oh, interesting. So we have another idea that the motion of the truck is going up the ramp. So if it was slowing down, it would sort of make sense that it would be going down the ramp. We have another idea that there's vertical arrows to earth and the other arrows are parallel to ramp. That is interesting as well. Those are all some excellent ideas. So let's take a look and analyze this. Which direction is the net force in? So the net force in this particular problem is parallel to the ramp. And it's parallel to the ramp and it's going downwards because the truck is slowing down as it's going up the ramp. So if you think about it, right, the truck's motion is going up the ramp. And so if it slows down, right, that means the truck has to basically accelerate backwards. And this allows the truck to safely come to a stop. We will draw a free body diagram. We will. Don't worry. We will. We aren't quite drawing it yet. We're just looking at the net force, but we will in a few minutes. So now this is where we draw the free body diagram. So what I want you to think about is we're going to analyze the net force. If the net force is indeed parallel to the ramp, what this means is that all the other forces, all the other directions should cancel out so that only a net force parallel to the ramp remains. So on your diagram, I want you to add in arrows indicating where you think the directions for the following forces are. So there are three forces that we're going to be analyzing: friction, normal, and gravity. I want you to draw a free body diagram on the picture that shows where these three forces are. Now remember, if you think about it, these arrows should basically more or less cancel out so that there is one net force remaining that is going down the ramp. So this is actually kind of tricky. And you're going to have to really think about where these forces are. So here is what your free body diagram might look like. So let's first start with the easiest one. The easiest one is going to be the friction force. That's because the friction force always directly opposes the direction of motion. So if the truck is going up the ramp, the friction force is going to be pulling the truck down. What about the force of gravity? Well, gravity always pulls objects straight down. It does not pull objects at an angle. That's something that can easily be misinterpreted. Gravity always pulls objects straight down. And the normal force is always perpendicular to the surface. So in this case, the normal force is perpendicular to the ramp. So it actually is pointing at an angle. So let's observe what is wonky about this. Notice how the normal force is not basically straight up. Right? In the previous stuff we've done, the normal force is straight up, gravity is straight down, normal force is equal to gravity, yada, yada. Notice how that's not the case. Notice here that is not the case. Notice here how the size of the force of normal force is not the same as the size of the gravitational force. Notice how the directions aren't even like perfectly like, aligned with each other. So this is where things get kind of wonky. So there's a few things that I want you to take away here. The normal force is always perpendicular to the surface, not perfectly straight up, but instead perpendicular at the surface. So if you have a surface that is like vertical, right, the normal force is going to be coming straight out. In this case, we have a ramp, so the normal force is perpendicular to the ramp. It's coming at an angle. Another takeaway here is that the force of gravity always pulls objects straight down. It does not care about angles. It just pulls them straight to the center of the earth. And the friction force always opposes the direction of motion. And since the truck is going up the ramp, the friction force is going to be pulling the truck down. So now I want you to quickly strategize in your graphic organizer. I want you to strategize what information you need in order to figure out the net force. So our goal here is to try to figure out the net force acting on the truck, which means we need other information. So this is where you determine, where you quickly, not determine, you quickly strategize what information do you need in order to figure out the net force. We're not going to solve for it yet. We're just going to strategize. What do we need to figure out? We need to figure out what forces do we need to figure out? How do we figure them out? So here's how I like to strategize is, so in order to figure out the net force, we definitely need to figure out the force of friction. Why do we need to figure out force of friction? Because the force of friction is, we know that it's parallel to the direction of motion. We know that it's going to be slowing down the truck. So we definitely need to figure out the force of friction. We definitely need to figure out. However, friction is dependent on the normal force. So in order to figure out the force of friction, we also need to figure out the normal force. So we need to figure out the force of friction. We need to figure out the normal force. Additionally, we also need a way to add and subtract all of our forces to figure out the net force. In order to figure out the normal force, we're also going to need the force of gravity. So basically, we need to sort of figure out the magnitudes of these forces and then figure out a way to add and subtract them to figure out the net force. So now I want you to sort of try to think about how you could figure out the normal force acting on the truck. How could you try to figure out the normal force acting on the truck? I will give you a hint in maybe 2 or 3 minutes. So how can you try to find the normal force acting on the truck? Okay, so here's the hint I will give you for those who need a hint. What I'm going to say is something, 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 something about triangles and something, 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 something about trigonometry, something, 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 something angles, something, 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 things are at angles, things look like triangles, things like trigonometry. Okay, so let's talk about how we can find the normal force. So in order to figure out the normal force, we definitely need to use gravity, but currently gravity is not really helpful for us. So right now, gravity is, because gravity is, in general, we want our forces to be parallel and perpendicular to the direction of motion. Gravity right now is not parallel or perpendicular. It's sort of at an angle compared to our direction of motion. That's not very helpful because, right, when we worked with X's and Y's, right, the reason why it was really easy because we know that Y never interferes with our X, and we know that our X never interferes with our Y. So we can just set them up, separate each other, and just work with each thing separately. But here, because gravity has an angle, gravity technically has an impact on both our parallel and our perpendicular directions of motions. So in order to make gravity helpful, we have to break down gravity into parallel and perpendicular components. Okay. So what I'm going to start doing this, I'm going to start doing this on the board here, how we can break this down. Okay. So please try to pay as close attention as possible. This is where things can get a little tricky. I'm going to try my best to explain this, but you know, I'm not perfect, so please forgive me if I'm not perfect. Okay. So first off, here is our ramp. It's at an angle. Here's the block. Here's our free body diagram. Our normal force going up, force of friction going down, and force of gravity going. So what we can do here is we can draw a triangle using the force of gravity as our hypotenuse. So let's draw a line that is perpendicular to the ramp, and let's draw another line that is parallel to the ramp. So if we can somehow break down this force of gravity into a perpendicular component and a parallel component, this would be perfect because now we can just combine them with these forces and we'll have a magical problem that we can magically solve. Okay, so the gravities are hypotenuse. This is one side and this is one side. And we need to somehow figure out how to break this down. Okay, so this is where we need to use a little bit of geometry. So if this angle is theta, and this first triangle is a right triangle, then this angle needs to be 90 minus theta, which makes this angle theta. Does that make sense? There's also the alternate interior angle hypothesis, whatever that thing is. It's like, you can also think of it as like, I don't really know how to, I don't remember the geometry theorem for this, but basically this theta, this angle is theta. So if we're drawing a line perpendicular to this makes, when this line is perpendicular to this. So this is gravity, it's perpendicular to the bottom of the ramp. So that means that this angle needs to be 90 minus theta. And so if this angle right here is a right angle, this angle needs to be theta. It's 90 minus theta plus 90. So how else can I explain this? Yeah, yeah, basically this angle is theta. Because this angle is a right angle, this angle has to be 90 minus theta, because this has to be a triangle, and that angles of a triangle add up to 180. And then which makes that this angle has to be theta, because all these angles also need to add up to 180. So this angle right here will be theta. Does that make sense? I can try to explain it more. I don't know how comfortable you are with geometry and stuff. I'm going to assume that that was okay. Okay. So now that we have that now that we know that this angle is theta, with the hypotenuse being the force of gravity, we can now figure out the perpendicular component, which will be mg cosine theta, and then the parallel component, which will be mg sine theta. So we now broke down the force of gravity into a perpendicular, into a parallel component. So in general, when you're working with forces at angles, you're going to want to figure out how to break them down into components that are parallel and perpendicular to the direction of motion. So in this particular case, force of gravity was coming in at an angle. So we broke it down we basically use trigonometry and geometry. You figure out what this angle of this triangle is, and then we broke it down into sine theta and sine theta. Okay, so now I want you all to try to solve for the net force while leaving everything in terms of coefficients. So like mg, coefficient of friction, mu k, leave all of those in terms of coefficients. See what you can do and try to solve for the net force now that we've broken down the force of gravity into parallel and perpendicular components. Okay, so I'm going to try to go through this now. Okay, so the first thing I'm going to introduce is a sort of a new kind of notation. So previously we used the net force. The net force is helpful because it sort of tells us that we're looking at an overall force in one particular direction. However, the net force can be misleading because it's sort of just because in reality it's not so much the net force as it is the sum of all forces. So the net force sort of tells us the overall force in one direction. And this is actually what this actually is the sum of all forces in that particular direction. We usually indicate this with sigma f. This is a sigma, the Greek letter, which means the sum of all. So the net force is really the sum of all forces in that direction. And this equals our mass times acceleration. The net force is the sum of all forces in that direction, which is equal our mass times acceleration in that direction. So I'm going to be using the sigma a lot more because this is how generally we use it. We usually don't use the net force. We usually use the sum of all forces. But the net force is helpful just to visualize that we're looking for an overall force in one particular direction. To solve for the forces in one particular direction, we need to look at the sum of all the forces in that direction. So we're going to first look at the perpendicular direction here. So we know that the net force of the perpendicular direction, in other words, the sum of all forces. So I'm going to indicate that we're looking at the perpendicular direction by putting a perpendicular sign. The sum of all forces in the perpendicular direction is going to be mass times acceleration. However, the truck is not accelerating above the ramp or below the ramp, so this is just going to be 0. So the sum of all forces, the net force in that direction, is going to be 0. So what are all the forces that comprise our perpendicular forces? We have, of course, the normal force, in one direction, and then we have our gravitational force that we decomposed in a perpendicular component. So our normal force minus mg cosine theta is equal to 0. So now we know our normal force. Normal force is just mg cosine theta. So now we can use this to figure out the net force in the parallel direction. So the net force in the parallel direction is the sum of all forces in the parallel direction, which is just the mass times acceleration. So this time, this is not 0. The acceleration is not 0 because we do know that there is a net force on the truck because the truck is indeed slowing down. So what are all the forces in the parallel direction? What's the sum of all the forces in the parallel direction? Well, we have the force of friction pointing down. And we also have the force of gravity also going down. So these are going to be in the same direction. The force of friction plus the force of gravity, mg sine theta, these are both in the same direction. It's going to equal our mass times acceleration. This is Superman force. The force of friction, if you remember, is the coefficient of kinetic friction times the normal force. This plus mg sine theta equals our mass times acceleration. And so normal force, if you remember, was previously our coefficient of kinetic friction times mg cosine theta plus mg sine theta is equal to our mass times acceleration in parallel direction. This right here, you definitely should not memorize this formula. It's actually much more helpful to be able to solve a problem. This is not even really a formula because this will change depending on the setup of the problem.
So what is parallel of F net? Net
Okay,
force.
this right here, this mass times acceleration, this is going to be our net force.
Okay.
So this whole thing is going to be our net force.
Wait, why do you know that the perpendicular force equals 0?
Okay, so if something is on a ramp, right, it's not going to be going. Something is on a ramp. Okay, so if this was a ramp and I had my chapstick going down a ramp, right? It's not going to be accelerating above the ramp. And that's not going to be accelerating through the ramp. It's accelerating down the ramp. So it's going down parallel to the ramp. It's not going above above. It's not going above the ramp or below the ramp. So sort of like if you were rolling something on a table, right? It's not going above the table. It's not going below the table. So imagine if this table was now just at an incline. So it's the exact same thing, right? It's going to be moving parallel to it, but it's not going to be accelerating above the ramp or below the ramp. If it was like flying, then it would be going above or below. But like if something is just rolling on the ramp, right? If it's not leaving the ramp, then there's not going to be any. There's not going to be a net force there. So basically, because it's just staying parallel to the ramp, it's not going to be going. There's not going to be a net force in that direction. If there was a net force in the perpendicular direction, then the truck would be accelerating above the ramp, like this, or going through the ramp. What does the mg sine theta represent? Mg sine theta is the force of gravity decomposed so that this is basically just it basically measures how much force of gravity is pulling an object down the ramp. So the force of gravity is pulling the object it's technically pulling the object at an angle. So we want to figure out how much the force of gravity is actually pulling it down the ramp. Because some of the forces of gravity is used to keep the object into the ramp, right? If there was no gravity, right, the object would not really touch the ramp, right? So some of the force of gravity is being used to pull the object into the ramp, and that's this mg cosine theta. Mg sine theta is how much the force of gravity is pulling the object down the ramp. Now we got that from decomposing gravity. Okay. So just to quickly recap what I did. I split our forces into, split our forces into parallel and perpendicular forces. I split the parallel forces, which is the force of friction, and mg sine theta, which I got from decomposing gravity into parallel and perpendicular components. And then I also examined the perpendicular forces, which is the normal force, and mg cosine theta, which was found from decomposing gravity into perpendicular component. So the perpendicular, the net force, the overall force in the perpendicular direction, the sum of all forces in the perpendicular direction is 0 because the object is not floating above the ramp, nor is it going into the ramp. It's just going down the ramp. And so the perpendicular net force is going to be 0, which means the force pulling it above the ramp, the normal force, is going to be the same as the force pushing it into the ramp, which is mg cosine theta. So that's how we know that our normal force is going to equal our mg cosine theta. Now we can take a look at our parallel force. We know that our net force is going to equal our mass times acceleration in the parallel direction. So the two components that comprise the parallel forces is the force of friction, which is pulling it down the ramp because it's going up, and then the force of gravity pulling it down the ramp. So they're both in the same direction, which is why you can add them. And so our mass times gravity times sine theta plus the force of friction will equal our mass times acceleration. And then you can further simplify the friction into mu k times the normal force. Okay, so now I'm going to just do a practice problem here. So this time we have a truck that is sliding down the ramp. So we have a truck of mass 1,000 that is allowed to slide down a ramp angled at 30 degrees with a coefficient of kinetic friction of 0.1. And let's figure out what is the acceleration of the truck. So this practice problem is going to be pretty much identical to what we just did, except this time the truck is going to be angled going upwards. The truck is going to be going upwards. So let's take a few minutes to try to figure this out. The truck is going to be going down the ramp. The truck is going down the ramp instead of going up. Okay, so I'm gonna just quickly go through this. Let's first draw a free body diagram for this. Once again, it's coming at an angle. It's how we know the angle, which is 30 degrees. So we have the normal force pointing straight up. This time, because we have the truck is sliding down the ramp, friction is going to be pulling up the ramp. And then our force of gravity is going to be pulling straight down, which we're going to decompose into mg cosine theta and mg sin theta. So notice here how the setup, the free body diagram looks very similar. In fact, the only thing that changed was the force of friction. Instead of pulling it down the ramp because it was going up, now because the truck is going down the ramp, but for force of friction is going to be pulling it up the ramp. So now let's figure out the net force in the perpendicular direction. So the net force in the perpendicular direction is going to be 0 again, because it's neither going above the ramp nor below the ramp. Net force, or in other words, the sum of all forces in the perpendicular direction is just going to be 0. So the force pulling above the ramp, the normal force, is just going to equal the force pulling into the ramp. It's just mg is going to be. This time for a parallel, once again, our net force is going to equal the sum of all forces in the parallel direction. And this is going to equal our mass times acceleration. So the sum of all forces here is going to be equal to the force of friction, which is mu k times this. Oh, actually, so let's first use the force of gravity pulling it down. So g sine theta is pulling it down. And then because friction is pulling up, it's going to be a minus. So we mu k. This is going to equal our mass. So this looks pretty much identical to the last problem, other than the fact that instead of a plus, there's going to be a minus here because they're not in the same direction anymore. So now let's turn this normal force into what we had previously. So mg sine theta minus mu k mg cosine theta equal to m times acceleration. We can actually cancel all of the masses out. So what's left is g sine theta minus 0.1 means g cosine theta is equal to acceleration. And I believe if you do this all out, you get that your acceleration is something like 4.06.
What is the capital M stand? Or no,
Capital-
is that oh, that's the coefficient of kinetic friction.
Yeah. This is like a huge. Does anyone else have any questions on anything that I covered today? This is kind of different because you have to really start separating things into parallel and perpendicular components. Previously, you can sort of sometimes just work in one dimension. You can just sort of, I just know that my normal force is equal to my force of gravity. Now you actually have to be more careful. You actually have to figure it out. I would not recommend memorizing anything here. I would not even remember memorizing the setup. I would not recommend memorizing anything here. I would instead think about how you can break things down into parallel and perpendicular components. Because sometimes we will be working with ramps, and sometimes instead of working with ramps, the forces will just be directed at an angle. And so that's something you should also consider. So there's going to be a lot of, so I would just remember that how important it is to break down forces into parallel and perpendicular components using trigonometry, and then separating, solving for the forces one at a time. And don't be afraid to use one force from the other side if you figured something out. So notice how here there was no magical one-step solution that figured everything out. I have to separate things in parallel. Use my answer here. So there's going to be a lot of problems throughout the year where it's going to be something similar, where you won't have one magical solution. You have to use one from the other. Sometimes, right, in this problem, we have two. Sometimes you may have three. Who knows, right? So sometimes you can only go so far with one step, and you have to use the results from that step into another step.
Why does it say 0.1?
Because that's the coefficient of kinetic friction in the problem.
No, it said 0.5.
Yeah, it says 0.5 for us.
Oh, sorry, I changed it. It used to be 0.5. I think I forgot to change it on the graphic organizer. It used to be 0.5, but when I actually did the math, it actually didn't make any sense. So 0.1, I had to change it to 0.1. If it was 0.5, the truck would actually start going up the ramp, which wouldn't make any sense. Yeah, sorry for that. Otherwise, in terms of, there's going to be a quick exit ticket. So I just want you to quickly answer, why is their normal force not equal to the force of gravity for a truck going up a ramp? So just quickly answer that, and then that'll be it for today. So no homework. Make sure you do your asynchronous survey tomorrow because it's Wednesday. And then other than that, that should be it. Yeah, I think that should be it.
Do we have to turn in the graphic organizer?
If you finished it, you should submit it, but yeah.
Okay.
Okay, so it's 9:55. If you finish the exit ticket, you are free to go. I will see you all on Friday. If you have any questions, you can hang around and ask me them. I'll be happy to answer them. This is kind of a